Video for 7.3. So far, we have learned how to solve a couple differential equations. One, just where it's straightforward, we can find the antiderivative. In 7.2, we looked at separable differential equations, so we could rewrite this all y's dy equal to all x's dx. If these first two options aren't an option, we have a third method for kind of handling solving differential equations called slope fields. And so slope fields give us a picture, an actual visual of the family of curves that make up the solution to differential equations. So if you remember, plus c is the general solution. That's because there's a family of functions that solve differential equations. So we're going to have dy dx of some function in terms of x and y's. So if we have dy dx equal to something in terms of x and y, remember dy dx is the slope. So we have the slope of the line that's tangent to the graph of the solution at that point, x and y. Okay, so a couple reminders, just graphically what to remember. If we have dy dx equals 0, that means our tangent line is horizontal at that point. So we're going to use just a short horizontal line to represent that. If dy dx is undefined, our tangent line is vertical at that point, but we are actually going to show nothing visually. Okay, so we are, how do I want to put this? We'll say leave blank. I don't want to put none because I don't want you guys to think that there is no slope. Okay, if our slope is positive, we're going to use a little upward line. Now, if it's positive 2, that should be steeper than positive 1/2, for example, but that's when we have positive slope of our tangent line. And then if it's negative, we're going to go the opposite way. Okay, so we're going to use these kind of like miniature line segments to kind of help us visualize what the slope of the tangent lines look like at each of these points. So when we are sketching a slope field, we are going to find kind of those big pieces. We're going to find where dy dx is 0, where it's undefined. We might have some patterns and some quadrants we can recognize, and when worse comes to worse, we just are going to substitute in some points for x and y. So, first example, we're going to consider this differential equation, okay? So using the slope field method, here's what we're going to do. We're going to sketch a slope field for this given differential equation at these 12 points that are marked, okay? So what we're going to do here first, I'm going to kind of do some work for A down here, you guys. So where is dy dx 0? Okay, because that's not kind of number one what they want me to find. Where is dy dx 0? So it is 0 for when x is 0. Well, where is x 0? All along the y-axis, right? So all along the y-axis, x is 0 at those points. So we are going to draw horizontal segments at those points. So here, oh, sorry, that's not one of my 12 points. I might come back and erase that one. Okay, where is dy dx undefined? Well, it is undefined when y equals 0, right? Because then I get division by 0. Well, where is y 0? On the x-axis. So actually, you guys, I don't need, we're going to scribble that one out. Don't want that one. Okay, so so I would have vertical tangent lines along here. This is what I mean by leave blank. We're actually not going to draw in any vertical segments. We're going to leave those blank. Okay, then let's find some other points. So here is kind of what I'm going to do. Because I have these points already given to me, I'm going to use those. So I'm going to kind of create a table here to keep track. So we've got x's, y's, and then what is the dy dx? Okay, so I have the point negative 1, 1. We have the point negative 1, 2. We've got negative 1, negative 1. Negative 1, negative 2. And then we have these over here on the side. So we've got 1, 1, 1, 2, 1, negative 1, and 1, negative 2. Okay, so what are dy dx at all those points? Well, I just plug these x's and y's in right here. So negative 1 squared is 1 divided by 1 is 1. Negative 1 squared is 1, divided by 2 is 1/2. Negative 1 squared is 1, divided by negative 1 is negative 1. Negative 1 squared is 1, divided by negative 2 is negative 1/2. 1 squared is 1, divided by 1 is 1. 1 squared is 1, divided by 2 is 1/2. 1 squared is 1, divided by negative 1 is negative 1. 1 squared is 1, divided by negative 2 is negative 1/2. So you could see there was a pattern kind of happening. We could pay attention to that too. Now what I'm going to do is I'm going to graph those slopes. So at negative 1, 1, we had a slope of 1. Okay? I'm going to do all my 1. So the other place I had a slope of 1 was at 1, 1. So I want to make those like look identical if I can. Okay? Then we had some slopes of negative 1, so it should be the same steepness, just the other way, at negative 1, negative 1, and at 1, negative 1. Sorry, I did those backwards. Okay, then we had some positive 1/2s, so I should make this less steep than this one, right? 1/2 is more shallow. Okay, it's also positive 1/2 at 1, 2, so again, I should make those look very similar. Then we have negative 1/2 and negative 1/2. Okay, so this is a slope field. It gives us a picture of the family of functions that could satisfy this differential equation. Okay, so now part B, and I didn't leave myself a ton of room, sorry guys, so I'm going to use up here a little bit too. Part B asks us to find a particular solution. We're going to go ahead and do that the same way we did in 7.2. I'm going to go ahead and rewrite my equation by separating my x's and y's. Okay, integrate. So we got y squared over 2 equals x cubed over 3 plus c. My particular solution they want me to find is f of 1 is 2, so we're going to plug in 2 for y. Do that down here. And 1 for x. So we've got 2 equals 1/3 plus c, so 5/3 is our c. So y squared over 2 equals x cubed over 3 plus 5/3. So there is our particular solution. We could solve this for y as well. I'm just going to write it out here. Because 1, 2 is positive, we just need the positive root. But I multiply everything by 2, then take the square root, so we would get 2/3 x cubed plus 10/3. So multiplied everything by 2, then took the square root. So, or that. Okay. Number 2. Draw the slope field that represents this solution or the family of solutions to this differential equation. Okay, so a couple things to note. Notice, since dy dx does not depend on y. Okay, so what we mean by that is there are no y's in this expression for dy dx. So dy dx only changes with respect to x. Y does not affect it. So what that means is that dy dx at all points that have this form, so x some number, x naught, some y that goes with it, are equal. So that means like when x is 1, so the point 1, 2, 1, 3, 1, negative 1, 1, negative 2, they all have the same slope. So all along that same vertical line, whatever x equals, those are all going to have the same slope. Okay, so let's go ahead and find kind of our starting point. We always like to find where is dy dx equal 0. Where does this happen? Okay, so I'm going to set this equal to 0. So we got x squared minus 2x minus 3 equals 0. This factors nicely to x is 3 or negative 1. Okay, so that's where our slopes are 0. So this is what this means. So all points, 3 with whatever y value and negative 1 with whatever y value, have slopes of 0 for their tangent lines. Tangent lines. Okay, so again, I'm going to draw those in. So at x equals 3, these all have horizontal tangent lines. Doesn't matter what the y's are. Okay, and then at -1, same thing. Horizontal tangent lines. Okay, so if you see this ever in a slope field, you guys, where along the same vertical line, they have the same slope, that means dy dx did not depend on y. We can do the same thing horizontally. If you have the same slope across the horizontal, the dy dx did not depend on x, okay? Also, dy dx for this particular problem is never undefined, right? This is defined for all reals. So we don't have any vertical tangent lines for this function. Okay, now we are going to look at what's happening like in between these, okay? So now we're going to investigate either side of x equals -1 and x equals 3. So again, I'm just going to plug in some values here, you guys. And I'm just going to do x and dy dx because the y's do not matter, right? So we have, let's see, we check on this side of -1. So let's do -2, 0, 1, 2, and then 4. Okay, so all I'm going to do is I'm plugging these in for x to see what is dy dx equal. I already went ahead and did this, you guys, but you can double check my math, okay? All right, so I am going to graph these slopes now. So at -2 and at 4, they have slopes of 5. So these are really pretty steep. So positive slope of 5. So -2, they all have the same. Again, I want to try and make them all look the same, if I can. Okay, also that same slope at 4, so I'm going to try and make it look at the same over here as well. Nice and steep, positive slope. Okay, now at 1 we had -4, so it's about the steep but going the other way. So at what did I say? Oh, +1, -4. So also pretty dang steep. A little less steep than the 5 if you can make it look like that. Okay, and then at 0 and 2 we had -3, so it should be a little less steep than this one. Again, trying to make all those ones look the same if we can. Same over here at 2. Oh, sorry, I'm at the wrong. Sorry, these ones are not over here. I didn't mark any points over here, so we can just ignore this step, okay? This is supposed to be at 0, is -3. Sorry, I missed my 0 right there. Okay, so now there's my slope field. So this, again, this represents the general solution. Now they want to use the slope field to draw a particular solution. Okay, so my particular solution is when x is 0 and y is 2. So I'm going to plot the point 0, 2. So 0, 2, right there. Now we are going to follow the slope field to the left and to the right until I reach the ends, okay? So what I mean is I kind of am going to treat these almost like mini asymptotes, is I'm going to try and follow a smooth curve. So I kind of am going to follow, and then I would reach here, and then I would fall outside this. Now I didn't graph anything over here, so I'm just going to kind of draw that down. My graph runs out. To the right, okay, I'm going to kind of come down. Sorry, let me go beneath here. So kind of staying between, I never want to touch any of the slope fields, but I'm kind of like following between them where it naturally keeps my curve smooth. We don't typically put the arrows on the ends of this, you guys. You'll be given like a field to just stay within. Sorry, I had some extra over here, so this is unnecessary piece. So I only kind of looked at this window. So we kind of like keep going until I can't anymore, but we don't use arrows because I don't necessarily know what the slope field looks like beyond this. So this blue graph I have represents the particular solution on a slope field. So that's how I find a particular solution when I'm not using integration or separating the variables and then integrating. We can actually represent it visually as well. Okay, last question. All right, which of these could be the differential equation that has this slope field? Okay, so one thing I want you to look for is look for patterns. So look vertically, look horizontally, look is there anywhere it is 0, look for anywhere it's undefined. So what I notice is vertically, these lines in this vertical line all have the same slope vertically. That is true all along here, same slope, same slope, same slope, same slope, all the way through. When that happens, this means dy dx is not dependent on y. So that's kind of what we had in that previous problem. So what this does is this eliminates any of the differentials that use y. So that's going to eliminate b and d. Okay? Now the other thing I can look at is I kind of have a pattern with where it's positive and negative. So over here, they're all negative slope. Over here, it's all positive slope. Okay, so, and then we got 0 here. All right, so let's see what happens here. So all my x's over here, you guys, are negative. So if I put in a negative negative, that's not going to give me negative slope. If I put in just x, well, x is already over here negative, so I would have negative slope. X over here is positive, so I would have positive slope. So that is why option C is the best fit for the slope field. Okay, that's all for 7.3, guys. Thanks for watching.